Okay, two conducting rings, radii r and 2 are uniformly in opposite directions. Velocity is 2v on a conducting surface S. Uniform magnetic field B. Okay, perpendicular to the plane of rings. The potential difference between the highest point of the two ring. Okay, so this point and that point, what's the potential difference between that? Fine. So it's a conducting surface. That means these two potentials will be equal. So we just need like what? This thing minus that thing. Cool. What do we know about potentials? Well, yeah, it's just uh, the change in flux upon change in time. Yeah, that should be potential, I guess. Sure. So in this case, the potential is just integration of EdL, not negative. Yeah, that should make sense. That's the EMF, I think. Yeah, right. Wait. Now, when we say the potential difference, wait a second. So isn't that like negative integral of EdL? That's gonna give us the potential difference. Isn't that right? Because yeah, then the E should be opposite. Wait a second. Yeah, I mean, like if the current is going in this direction, then there should be a potential drop. That's what we say generally. Uh, oh wait. Oh no. Okay, okay, I get it. The potential difference, that's just the potential difference due to the charges that got built up. It has nothing to do with the EMF whatsoever. Right. Cool. So yeah, what was I saying? So we can calculate it by using this thing. That consider just a small charge carrier on this thing. It's moving with velocity v, and there's magnetic field B in this direction. It's out of the plane, so V cross B, that's gonna be in this direction, right? Yeah, so we need a field in that direction, and with what magnitude? We want E equal to BV, so we want a field in that direction, and then it should be like, yeah, E vector is that. Cool. And in that case, the potential will just be the integration of E dl. Yeah, that's what this. Huh, is that right? That's the field because of, so the field is upward. That means this is higher potential, this is lower potential. You know what, whatever, just look at the magnitudes. That's it, that's what I'm going to do. So this will be what should actually be E vector dot L vector, which is like E vector dot L vector because E is constant. So that's going to be what, BV, I should say B cross V. Yeah, because it's like negative of V cross B. That's gonna be B cross V dot L. Okay, that's cool. So since all of these are just like perpendicular to each other, right? This is L vector, that's V vector, the B vector is coming out. All these are just perpendicular. So this is going to be equal to BVL. Cool. Yeah. So in this case, L is like 4R. So this is 4BVR. And over here, you got B and then 2V and then 2R. So that's still 4BVR. Oh, that's nice. Now, it would be negative in that case because the velocity is like actually negative 2V considering the sign convention. So this should be what, 8 BVR? That's the magnitude. Right, next question. Two coils X and Y are linked such that EMF E is induced in Y. So it has EMF E when the current in X is changing at a rate. So this is the rate di by dt. So current I, right? That's what it's in that direction. So if current I naught is made to flow through Y, fine. So if there's di by dt current change, then that gives EMF E. So we know that the flux, that's going to be M times I. So M di by dt, or I should say M I dot That's the change in flux upon change in time. That's going to be what? The EMF. Yeah, cool. So this is going to be equal to E. So now you know what this I dot is. Well, okay, we don't want the I dot. What do we want? We want M, of course, because that's what's not given. So M equal to E upon I dot. Okay, cool. And then they ask if current I naught is now made to flow through Y. The flux linked with. Okay, cool. So it's just going to be M I naught. But we know what M is. It's just E upon I dot and that times I naught. So E upon I dot. I naught. Well, yeah, that should be cool. Okay, next. A conductor AB of length L oriented along the x-axis moves. Wait, just draw this. So a conductor of length L moves in the xy plane with velocity. A magnetic field exists in this region. Okay, cool. So you gave us the velocity, which is probably the velocity of this center of mass, or it completely all of the points over there translate with that velocity. And magnetic field is given. Okay, the induced EMF will be fine. So it's still the same thing, right? It's just integration of what? B vector cross V vector dot dl vector, right? Yeah, well, yeah, that should be correct. Which because like these two are constant, so we can just say it's B vector cross V vector dot L vector, right? Cool. So this is like what? This is B vector is just 1 comma 1 but B naught, and this is V naught, so V naught B naught, and this cross 1 comma minus 1, and then dot L vector, which is, well, yeah, so L and then 1. That should be doing it 0. So it's what, like this and that, but with K, but there's no K over there. Oh no. So it's all just 0. I mean, okay, cool. That makes sense because V vector, B vector, these are like in that plane. So the force on each charged carrier, that's going to be up or down. And this length, it's in that plane. So it's, yeah, this doesn't make sense. So it's going to be 0. Cool. Right, next question. A metallic rod of length L and mass M is moving under the action of two unequal forces. Okay, the opposite to each other, acting at its end along the length. So just say like this is the rod, there's this F1 force, there's the F2 force. Specific charge of electrons is given. We don't want this statement, it's not any useful. Potential difference between the ends of the rod in steady state. Okay, so steady state, that means with respect to this rod, the electrons. Wait, this doesn't make sense. How can you even say steady state? Steady state of what? Like, this guy will accelerate all the time. It's never going to be at a constant velocity. So, what do they mean by steady state? Like, maybe the distribution of charges over here stays constant. Okay, that distribution with respect to this rod, maybe that's what they mean. Okay, cool. Well, that makes sense. Yeah, so how do we solve this then? The charges must not move, I think. Sure. How can the charges move in a metal? What charges move actually? It's just the electrons, it's not the protons, because they are like, yeah, that's how the root model works. Isn't that right? The protons don't move, electrons do. But then once again, that's when electrons can come and go. Over here it's stationary charges and stuff. But yeah, like if the proton started to move, that would make this thing extend. All right. Well, okay, let's just deal with the fact that the electrons won't move, because I think those are the ones that can move when influenced by the electric field or whatever field you have, and that should be making sense. So like I think it's like there will be a charge distribution and because of that there will be a field, and that field will make the electrons accelerate with the same acceleration as the rod, and that should make sense. What about the protons? They are bound by intermolecular interactions. So like I don't know, they are not just floating in space like electrons are. Actually, even electrons are not floating, they are like constantly colliding and stuff. So we are actually talking about the averaged motion of these electrons, right? So you know what the root model says? It says that the current, that would just be the acceleration times this tau, which is like the average time before which an electron hits some other particle, right? So since we want current to be zero, we want this thing to be equal to zero, right? And yeah, like not that the electron is not moving, but that it's not moving with respect to the rod. That should make sense. That looks right. Okay, so this cannot be zero, this can be. So we want its acceleration with respect to rod to be zero, right? The supposed acceleration, that is, if it was just not if it was just what should I say? If it was not doing that random motion and it was just like going in a simple path, that acceleration, you get it what I'm saying? Fine. So let's think about the electron, and we are the rod, we are moving with acceleration a. Then you have a pseudo force over there, ma, and you also, we have a field, right? That's what we assume. So E times E, that will be the field, and the total acceleration must be zero, so you should have E equal to ma. Oh, that's cool. And what is this a? Oh yeah, we can find that out. It will just be f1 minus f2 upon, like, if f1 is bigger, that is, upon the total mass of the rod, I think, right? Yeah, that looks right. And like, okay, cool, this side is positive, this should also be positive. Don't talk about vectors, talk about magnitudes. That should be cool. Okay, and what do they want? Potential difference between the ends of the rod in steady state. So we got the field like that, just multiplied by the length of this rod, and that's gonna give us the potentials. Like this will be our potential multiplied by L over there as well, ml. So that goes like that. Okay, cool. So what's this thing? No, this is wrong. Upon em ml. All right. Yeah, this thing is like a vector thing. Oh, oops. So this is wrong and this is correct. Okay, next question. This was a nice question, really. I mean, it's weird that you just accelerated a rod and suddenly there are potential differences in it. It is weird. Okay, whatever, next question. Two parallel rigid wires are fixed at distance d. Draw this thing. Two parallel rigid wires, distance d, with each wire in a vertical position. Okay, the top ends of the two wires are connected through an ideal inductor of, okay, cool, top ends are connected by an inductor. A straight connector of the mass m can slide, okay, cool, can slide freely up and down, maintaining electrical, okay, I get it. Horizontal position, that means there's gravity acting. A uniform magnetic field exists perpendicular to the plane of wire. Obviously, if the connector is released from rest, the graph of its downward velocity time will be. So, okay, let's try to think about it. Apply Faraday's laws first of all. That if this like current, actually first of all, talk about length and area. So dl vector, that will be going in the clockwise direction, and that according to that the area is the area vector is pointing, it doesn't matter because we don't know the direction of magnetic field anyway. Yeah. Okay. Fine. And then if you think about it, the flux, yeah, if the current is going with, okay, this is not correct. Like whatever, just think about that. So the flux through this thing, that's gonna be what, b times the area of this thing. You know what, call this thing x and call this thing, it was d, right? Yeah, so x times d, that's the flux. Okay, plus uh what, this thing, that's also producing flux over there. It's gonna say it's like li, yeah, that should be correct. So that's the flux. Okay, cool. So the negative change in flux, that's equal to integration of EDL. That means integration of EDL plus the derivative of flux with respect to time. That will be 0. What's integration of EDL? Oh, wait, no resistors. Oh, that makes sense. It's, yeah, so there we go. No resistors, that means it's just 0. Oh, that was weird. So it's equal to 0. Oh, no, not that. The derivative of this thing. And that's better. So d and d don't change. Dx by dt, that's just v. And that's equal to what? Negative L di by dt. Right, that's cool. So that's one equation that you got over there. We also have another equation for this mass, that if there's current I going in it, now we really need to think about positions and stuff. So let's say the current is going clockwise, the area vector is going in and stuff, right? And just for the sake of calculation, let's say that the magnetic field vector is also going inside, right? Alright, so the flux will still be positive because of this L, and now you got this positive flux pxd, alright, and then the current is going in that direction. So if this is going inside, magnetic field's inside, current for this guy is going in the right, no, in the left, yeah, so current cross magnetic field, that will, wait, what, right, so there's force in that direction. Now it can be negative or positive, so it's, yeah, of course it depends, but the thing is that it's in that direction. So what is this force? It's just the length of this thing, which is d, times the current I times the magnetic field, right? Cool. So that's that force plus mg, that's another force. So that's equal to m times acceleration, and acceleration is like, yeah, whatever, just think about it like that. So that's another equation that you got. Okay, now how do we use this? Oh, there's a di by dt over there, and we got I from that. Or we could just differentiate this thing and then put di by dt into that. That's better, I think. So just differentiate this thing. So it becomes what? dB. Now this d is different, right? It's the quantity d, and then di by dt. Alright, that's equal to what? mda by dt. Okay, da by dt. The first time I have seen this anywhere. Fine. Mg is just gone, so it's gonna be what? Mda by dt. Alright, cool. And we can put okay, this goes over there. So di by dt is also this thing, so put that over there. P d and oh, negative b squared d squared v upon l. Well, that's sweet. That's equal to mda by dt, right? And now we have successfully eliminated current from this thing, and we just got it in terms of what? In terms of velocity, acceleration, those things. Okay, cool. Now what? Let's try to write in one variable. Acceleration is what? dv by dt. So this will be what? D squared v upon dt squared. It's still problematic. How are we going to solve this? Have I seen things like these? Second derivative is some linear function of the wait. Yes, I've seen these. Oh yeah, of course. It's an SHM. Ah, yep. It's SHM basically. So, because it's an SHM, it should be like what? V is V naught sine omega t, something like that. Uh, yeah, and then plugging that back into something else. Oh, that's sweet. Plugging that into that, you get that current is also some kind of sinusoidal function with respect of time, of course. And all right. So I like to believe that all of these will have like sinusoidal functions, basically. That's nice. That's nice. But did we solve the problem? Let's look at the problem again. Okay. If the connector is released from rest, the graph of its downward velocity. So from rest, that means initially it's what? Its velocity was 0, right? So you are entitled to say that yeah, v is just v naught sine omega t, something like that, because initially there was no velocity. Cool. So it's downward velocity with time. Oh, we just found that it's gonna be what? Sinusoidal. Okay, next. A rod closing the circuit as shown in the figure moves along a U shaped wire at constant speed V under the action of the force F. Huh. Wait, constant speed under the action of force F. F is not constant in that case, right? Okay, cool. The circuit is in uniform magnetic field perpendicular to the plane. Calculate F if the rate of. Okay. Heat generation. Talk about heat and energy. What's the work done on this circuit? Well, we are doing the work by moving this thing. So it's F, and any resistances over there so that it can dissipate energy out? No, nothing, right? It doesn't heat up or anything. The only output it can, like, yeah, the only way it can lose energy is by radiating into the surrounding, and that's this thing, the heat generation, Q. So there's no way it can get energy by it. Is that right? Yeah, well, that should be right, because nothing about the specific parts are changing, and it's only that heat's being generated. That means that all the work that we are doing on this circuit, yeah, that gets transferred to heat. What's the work that we are doing? F times V. Okay, that's the power, but heat, yeah, Q is also like power, isn't it? Okay, that's nice. So F times V equal to Q. That was easy. So what are we trying to find? Calculate F. It's going to be what? Q by V. Cool. Two parallel long straight conductors lie on smooth surface. Draw this. Two parallel long straight conductors on smooth surface. Two other parallel conductors rest on them at right angles. Okay, I've seen this construction. A uniform magnetic field B exists at right angles to the plane. Okay, cool. They start moving out with constant velocity V. Constant velocity V. Which one? Maybe this one? Or like, and what do they mean by they? This is stupid. Okay, if R is the resistance per. Okay, that's fine. There's resistance over there. Okay. Current in the circuit will be. Oh god. Well, we can calculate one thing. We can calculate the EMF, of course. Yeah. So, what's the EMF? Like, let's say that this uh, right now it's like a square, isn't it? This length is L and this is X, so area is Lx and the flux will be Blx, so its derivative is like what, Blv. That's going to be our EMF, so that's I times R. What do we want to find really? Constant velocity. All right, if I is the current, yeah, we just want to find the current. So we got this thing, BLV equal to IR. V is constant, L is constant, B is constant. You can easily find out the current from this thing. What's the big thing? Oh, yeah, this changes. This is like what? I R, which is current per unit length, that times the length, which in this case is like 2L plus 2X. That's right. Okay, cool. Huh. Yeah, that's right. So now we want to find the current. Just divide it by that. Yeah. 12 plus 2X. What do they mean by they? Wait a second. Could it be that by they mean all four of these start moving out with each of them having velocity v? Well, that would be bad. Oh shit. Oh no. So then in that case, BLX, the derivative of that thing would be BL dx by dt, which would be in this case 2v, and then plus yeah, it's like x, okay, just say L. That will be BL 2v once again. That will be the total thing. So it's gonna be what? 4 BLV? That's bad. I don't get it. What are these people trying to tell us? And this should be equal to what? Okay, 4L times R times I. Okay, fine. These 4 get cancelled and then L also get cancelled. So I is BV upon R. Oh, that's nice. That's a problem. Oh, that came out nice somehow. Next, there is a uniform magnetic field B normal to the xy plane. A conductor ABC has length AB equal to L1 parallel to the x-axis. Okay, this is the figure. L2 parallel to the y-axis. ABC moves in the xy plane with velocity. Fine. The potential difference between A and C is proportional to. This shouldn't be that bad. Yeah. Potential difference between A and B is fine. It's like no big deal. Just find out the field that must be present so that this doesn't change its charge distribution. What is this? Like magnetic field V, and you also know the velocity. We have already done this so many times. It's just B cross V dot L. Yeah. So B in this case is, well, it's normal. You know what? Actually, instead of writing it like this, I will write it like this: BVL. Is that the right syntax? I don't know. A cross B cross C. Like for example, I cross J dot K, that will give us 1. What about the determinant 1 1 1? Like it's basically this thing. What will this determinant give us? This times that's gone. All right. Then that, wait, what? This is stupid. Oh, sorry, this is not right. It's 0 1 and then 0 1. Of course, this is just going to be 1. Yeah, that means yeah, it should be like A cross B dot. Of course, it's like that. A cross B dot C. That's written as this determinant, ABC. Cool. That's how it should be. All right. So, what do we have? This thing. We know we can like rotate this. So we can say VL and then that times B. Oh, that's nice. So this will be what? V cross L vector dot B vector. What's V cross L? So you got Vx Vy and let's draw this thing. Vx Vy and cross L vector is what? L1 L2. So it will be L2 Vx minus, okay, L2 Vx minus L1 Vy. Right, this complete thing dot um oh, all this times k hat, and that times okay, of course it's going to be like this because it's normal. That makes sense. That's the magnitude, or I should say, yeah, it's the magnitude. So it's proportional to, okay, we don't even need this thing then. So L2 Vx, which is over here, okay, of course this is the right one. Okay, cool. Next, an equilateral triangle. Okay, cool. Time t equal to 0, side DC is at edge of the magnetic field, is perpendicular to, okay, fine. The induced current versus time graph will be induced current versus time graph, so more like induced EMF versus time. uh yeah, it's like magnetic field is constant, so change in the area, that will be these small strips, those are the change in the area upon change in time. Change in time is same for each strip of same thickness, so it's proportional to what? This length. And what is that length proportional to? Yeah, the amount of thing that's inside. So at first it's very big and then it starts to decrease and then goes to 0. Right, cool. So it should be this thing. It varies linearly, of course. Okay, in a circuit shown in the figure, a conducting wire HE is moved with constant speed V towards left. HE, constant speed V towards left. The complete circuit is placed in a uniform magnetic field perpendicular to plane of circuit directed in inward. Okay, cool. The current in HKDE, this loop. Fine. What's the current in that? Cool. So let's choose our DL, and so it's going inside. I'm gonna choose this as the DL vector direction for the first one, and that is, so talk about the clockwise currents. Call this thing I1, this thing is I2. All right, cool. So what do you have? RI1. Wait, did they say anything about the resistance of this thing? No, they didn't. Conducting wire, not a resistance. Okay, so it's Ri, that's the EMF. That's integration EDL, and that's okay, that plus d flux by dt. So the area vector is going down, that means it's just B times whatever area is this over there. So BLV, that should make sense, but in this case negative BLV, so we can say it's equal to BLV, where this thing is L, of course. So BLV, cool. And over here it's going to be what? Positive BLV. So BLV equal to 0, and then you got what? This current I2, you got some potential. Okay, we need to talk about the charge over there. This is like Q, this is minus Q, so Q upon C plus BLV, that should be equal to 0. Yeah, that makes sense. Of course. Right. And now what? You got this thing. Now what do we do? Oh, these potentials are also, of course these are equal. Wait, what? No, that doesn't make sense. That is not right. There is something's wrong. There's some charge over there. Hey, this is a constant quantity. This should also be a constant quantity. So this current in here is just 0. There's a constant charge over there, right? And there's a constant current flowing in that. Cool. So I1 equal to BLV. I should just say I. That's the only current. And you got Q equal to negative BLV times C. Yeah, these are the two equations that we need. Right. So what do we want? Complete circuit is okay. Current in HKDE. That's 0. We just saw that. I thought they were going to ask what some other current, but whatever. Alright, next question. Wait a second. Next question is, when a J-shaped conducting rod is diagram, cool, is rotating in its own plane with constant angular velocity omega. What? J-shaped. This is the J-shaped thing. Constant angular velocity omega. About this point, I suppose. Alright. Okay, cool. The uniform magnetic field P directed normally to the plane of paper. Right. Then the magnitude of EMF induced across it will be. Right, cool. So yeah, if we are assuming steady state and then there's that kind of thing that charges are not moving with respect to this thing, or I should say they are moving such that they are on that location, like they are also going circular motion. Cool. So what should I say? Yeah, like m omega squared r equal to, what should I say, omega squared r, that's the acceleration. Yeah, in this case it's going to be different. Like whatever velocity it has over there, that's going to be what, omega r. Call this thing r. Actually, you know what, let's not think about just this little piece of wire. Let's think about any goddamn particle that's going around this in circular motion and has some charge q. Actually, yeah, we don't need to write that. So it's a distance r over there, so omega r is the velocity over there, and it wants centripetal acceleration omega squared r. All right, that's cool. Yeah, so what's the force? Magnetic field is going inside, so right hand rule says, this is stupid, yeah, it should be pointing radially outward. Okay, cool. So you have b omega r pointing radially outward. That means you want E times the charge, of course, that times q. Yeah, that times q. Okay, so E times q, that's equal to q times b omega r plus m omega squared r. Yeah, that's right. Of course. And now what? So you got this field, it depends on charge. In this case, the charges that we are talking about are electrons. So this should be the correct thing, right? Oh, no, it should be negative, right? Because, yeah, that's right. Uh, okay, so you got what? E equal to b omega r minus m omega squared r upon E, right? Alright, cool. And now what do we want? And yeah, this E thing is radially inward, so integration EDL. Then the magnitude of the EMF induced across it will be, okay, we just want the magnitude, so this field times this length, that should be doing it. Yeah, I suppose. Are we right on saying that? Well, this thing is for each and every particle. So like at this point, at this point, at every point, we should have this equal to that, Ah, we know E is in the radial inward direction. Just know it. Okay. So we can think about it's like, I don't know, something like, oh yeah, well that would be nice if it's in the, and then that times dl vector. It's somehow related to like this thing r dr vectors, of course. You know that this thing gives something about the area, right? Actually half of this thing, that's the area. But it's something similar over there, that you got this, like think about this length. It will be all right, e times l, that will be the voltage, cool. But then you also got this thing over here, e is pointing in that direction, but then the dl vector is going in that direction. So essentially you are tracing this area thing, right? That makes sense. Ah, but then there's magnitude. Oh, that's even better, because now it's all right, it's proportional to r. Heck yes, that's sweet. That's just sweet. You know what, let's do this. You can say e vector is, now we should have negative r vector, so it should be what, like r vector m by e omega squared minus b omega. Yeah, that's how it's gonna be. So when we say integration of e vector dot dr vector uh, for this line, you are essentially saying, well, all that stuff times integration of r vector dot dr vector, which is the area, which is this. Okay, 2 times of that area, I agree. So what's that? 2 times of area, just say a times all that stuff. Yeah, what was that, all that stuff? uh Omega m by e omega minus b, but that's not there. Wow. Magnitude of induced emf, something's not right, isn't that right? Huh? Wait, what? Oh come on, you know it wants to go in that. Oh wait, but is it going clockwise or anti-clockwise? Oh no, is it going clockwise or anti-clockwise? Is omega pointing up or not? And we just want the magnitude. Ah no, what about all that stuff? This is bad, this is really bad. Oh no. If cross it will be, why is there half everywhere and stuff? And we just want what, like a omega, so huh? Ah, just be the area. Yeah, like half of that would be the area. So this is twice of that, of course. It's 2 times of the area, and the area over here is, well, it's a J shape and it's right angles over there, isn't that right? These are right angles, so it's just what, this length times that length. Well, this is L, this is that L, it's L L, that's this, okay, half of that. And then you got this thing, which is plus half of pi r squared, and that's L by 2 squared. All right, cool. But 2 times of all that stuff, this is gone. So you got LL plus pi L squared by 4. Is it proportional to that? No, it's not. Why? Hmm. Cross it will be. No, I don't think it should be any of these things. Right. No, this is just not right. Application of ETR. Oh god. EMF induced. That should be this thing. Or not. What's the problem with this thing? Right, I'm and what EMF are they even talking about? Are they talking about like the EMF due to the conservative charges or the total EMF, which is or the induced? Okay, total EMF is of course just zero because the charges are not moving. Or are they talking only about the induced EMF? I don't know. Now what do I do? Okay, fine, just leave this question for now. Okay, next question. A rectangular coil of single turn having area A. Rectangular, wait, where did I go? Rectangular coil, single turn. Area A rotates in a uniform magnetic field B. Angular velocity omega about x is perpendicular to the field if initially the plane of coil. X is perpendicular to the field. This is the axis. Field is perpendicular to it. Okay, cool. No big thing. If initially the plane of the coil is perpendicular to the field. Oh, that's nice. So no flux. Average induced EMF when it has rotated. Wait, average induced EMF. Huh. Rotated through 90 degrees is uh, average induced EMF. Okay. How do we calculate that? The EMF at every point averaged. I think that's what they mean. What's the EMF at every point? What's the EMF at? Actually, just take a top view of this thing. This is basically the sheet. You got an axis over there, some angle theta, right? Maybe like, yeah, the field is going in that direction. Okay, no. Initially, field is like say 90 degrees, so it's going in this direction, and then as you move this, right, it has some theta over there, and then it moves. So it's 90 degree. After that, and what's the average thing? What's the flux? B A, it's cross, right? It's cross product. Area vector is going in that direction. Magnetic field is going in that direction. This is theta. That means this has theta. This is 90 minus theta. It's like cosine theta. Doesn't matter. It's the same integral. Right? Cool. So what are we talking about? How is the average gonna work? Integration of cosine theta dt. Isn't that right? Yeah, like that should be right. Upon the total time required. So it's like from 0 to t. Yeah, or I should say like, okay, from 0 to theta equal to 90 degrees. And it's integration of dt from 0 to theta equal to 90 degrees, something like that. Cool. But we know that theta is omega t. So you can say t equal to theta upon omega. Putting that over there, this just becomes this thing, d theta d theta. So integration of cosine theta, that's just sine theta, and then 0 to 90, that's going to be 1 upon this thing. I should say pi by 2, like whatever. And this thing over there will be pi by 2. This upon pi by 2. That's going to be what? 2 by pi. And the same thing will happen for sine theta as well, right? Because it's going to be negative cosine theta, and then negative of 0 minus 1. That's still 1. And over here, it's still pi by 2. So yeah, it's 2 by pi. And where's the question? Where did it go? Oh, here. Right, that's 2 by pi, but that's not the only thing. We want BA. So 2BA upon pi. That's better. Cool. What's with the omega? That's weird. There should not be an omega. Wait a second. Oh yeah, of course. It's not the flux, it's the derivative of the flux, right? And the derivative of flux with respect to time, of course, that will be omega ba sine theta with minus. So this will average up to 2 by pi. So it will be negative. Okay, this is gone. Magnitude omega, yeah, 2 omega ba upon pi. There we go. Next question. Right. Next we have a ring of resistance 10 ohm, radius 10 centimeter. So just write that down. Actually, you know what? That's better. Okay, resistance is 10, radius is 10 centimeter, which is 0.1. 100 turns and equal to 100 in is rotated at the rate 100 revolutions per second, about a fixed axis. So find omega is 100 cycle per second. Okay, which is perpendicular to uniform magnetic field. Magnetic field is 10. Wait, what? 10 mt? That means 10 milli should be better. So 10 power negative 2. The amplitude of the current in the loop will be nearly amplitude. Yeah, so that's like what, b times, so instead of the sine theta, all that stuff, like omega b a, that's the amplitude. Yeah, cool. In this case, a is like what, pi r squared, right? Okay, cool. Oh, resistance is also given. The amplitude of the current, right? So this upon the resistance, that will be our current. Yes. Yeah, right, cool. Oh, that times n, of course, because yeah, pi r squared times n, that's the actual area, right? So that's the current. Just calculate this thing. N is 100, omega is, you know what, no, I don't want that. I just want like what, 100 times 2 pi times beta, which is, oh, not beta, b, 10 power 82, and pi r squared. R squared is 10 power negative 2 once again upon r, which is 10. Oh, this cancels, cool. So 4 pi squared by 10, and they said that pi squared is 10, so then this cancels, she's got 4. Huh? Is that right? Oh, sorry, why should it be 4? It's 2 over there. So yeah, 2 so sorry, 2 pi squared by 10, this cancels, you just get 2. Why was there 4? So 2, that's the answer, right? Cool. A copper ball AP of length L pivoted at point diagram, cool, rotates at constant angular velocity omega at right angles to a uniform magnetic field of, it's a copper rod, pivoted at point A, constant angular velocity, right angles to the uniform field. Yeah, the EMF developed between the midpoint C of the rod and B. Oh, this and that. And in this case, is the EMF once again. Like, what EMF are we talking about? The it's just motional EMF, right? So it's the EMF required for the electrons to be in that way. God, should I do this? I mean, it's gonna involve that mass over there and stuff, which is something I don't want. Its acceleration should be 0. I get it, but won't that involve the mass as well? What do they mean by EMF? We do mean the conservative field because of the charge distribution, right? Or do we mean something else? Do we just mean the EMF because of the magnetic field? Like, yeah, that's what you mean? I don't get it. A loop like that. Wait, I think I've done something similar sometime. Oh yeah. Oh yeah, I think I've done something similar at some point. Wait, just wait a second. The electron is going through random motion, and that means, of course, with respect to whatever is happening at that point. Oh, that's complicated. So it's with respect to the rod in that case, right? Well, but according to that, because that part of the rod is actually going through some kind of acceleration, so the electron should have the reverse acceleration, the pseudo force, of course. This is getting complicated. You know what? I think I'm just gonna stop over here because these two questions I don't understand very well. This happened before as well, over here and then over here. Yeah, whatever. I'll just stop. Okay, see you in the next video.